Scientists may have found a planet more than 120 light-years away whose atmosphere contains a molecule associated with one of the strangest smells on Earth. Something reminiscent of rotten eggs, garlic, or decaying organic matter. And if that chemical signal is eventually confirmed, it could become one of the most important clues in the search for life beyond Earth. The molecule is called dimethyl sulfide, or DMS. On Earth, much of the DMS in our atmosphere is connected to biological activity, especially microorganisms living in the oceans. Tiny marine organisms produce chemicals that eventually enter the atmosphere, carrying a faint chemical fingerprint of life with them. Now astronomers have reported possible evidence of the same molecule in the atmosphere of K2-18b, a world located roughly 124 light-years away. But there is an important distinction. Scientists have not discovered alien life. They have detected a possible chemical signal that, on Earth, is strongly associated with life. Those two statements are very different. K2-18b is one of the most fascinating planets ever studied. It is considerably more massive than Earth and appears to belong to a class of worlds sometimes described as Hycean planets. Planets that could potentially possess a hydrogen-rich atmosphere and a global ocean beneath it. Imagine a planet covered almost entirely by water, wrapped in a thick atmosphere of hydrogen, drifting around another star more than 100 light-years from our solar system. That is the kind of world scientists are trying to understand. When the James Webb Space Telescope first examined K2-18b, astronomers noticed unusual chemical signatures in its atmosphere. Among them was a possible indication of dimethyl sulfide. The signal was intriguing, but it was nowhere near enough to announce the discovery of life. The observations were difficult. The planet is incredibly distant, the star is overwhelmingly brighter than the planet, and atmospheric signals are buried inside extremely faint changes in starlight. So scientists kept looking. Additional observations were made using different instruments and different wavelength ranges. Those observations produced further evidence consistent with DMS and possibly another related molecule, dimethyl disulfide. That made the situation much more interesting. But it still did not turn the planet into an alien ocean filled with microorganisms. Other researchers have warned that the evidence remains uncertain and that the chemistry of distant planets can be complicated. Molecules that appear strongly connected with biology on Earth might have other pathways under conditions we have never encountered naturally on our own planet. That is why scientists are cautious. And honestly, that caution is what makes the story even more fascinating. Real science does not work by finding one exciting signal and immediately declaring victory. It works by trying to destroy your own explanation. If another observation produces the same result, confidence increases. If independent instruments detect the same molecule, confidence increases again. If laboratory experiments show that the molecule cannot easily form without biology, the case becomes stronger. And if future telescopes repeatedly detect the same combination of gases, the evidence could eventually become extraordinary. That is the real story behind K2-18b. But this is only one part of a much bigger revolution happening in astronomy. The James Webb Space Telescope is transforming the way we study planets around other stars. One of the most exciting nearby targets is the Alpha Centauri system. It is the closest star system to our own, only a few light-years away, which makes every possible planet there incredibly interesting. Astronomers have reported evidence for a possible planet around Alpha Centauri A star remarkably similar to our Sun. The candidate appears to be a giant planet on a wide orbit. It has not yet been securely confirmed, and follow-up observations have struggled to find it again. But that does not necessarily mean the original detection was wrong. Planetary orbits can place a world behind or very close to its host star from our perspective, making direct observations extremely difficult. If the candidate is eventually confirmed, It would be an astonishing discovery because Alpha Centauri is practically our cosmic backyard. A planet around one of those stars would demonstrate that planetary systems exist even around the stars closest to us. And if a giant planet is there, smaller rocky planets could potentially exist farther inside the system. We simply may not have detected them yet. Then there are worlds much closer than K218b that could become major targets for future telescopes. One example is GJ357b, a nearby planet that has attracted attention because improved measurements have changed our understanding of its mass and composition. The lesson from cases like this is incredibly important. Sometimes a planet does not change. Our measurement of the planet changes. As instruments become more sensitive and astronomers combine observations from different telescopes, estimates of mass, density, and composition can shift dramatically. And one number can completely change the scientific interpretation of a world. A planet that originally appears to be a small Neptune could turn out to be something much more terrestrial. That distinction matters because rocky planets are among the most important targets in the search for life. A gas giant may have an incredible atmosphere, but it is unlikely to provide a solid surface where life like ours could exist. A rocky planet with liquid water and a stable atmosphere is a completely different story. That brings us to one of the most closely watched planetary systems ever discovered, TRAPPIST-1. 7 roughly Earth-sized planets orbit a small red dwarf star about 40 light-years away. When the system was announced, it immediately became one of the most exciting places in astronomy. Several of its planets lie within or near the star's habitable zone. But JWST has also delivered an important warning. Being in the habitable zone does not automatically mean a planet is habitable. The inner planets of TRAPPIST-1 appear to have lost much, or perhaps all, of their atmospheres. The intense radiation from their small red dwarf star may have stripped away the gases surrounding them. That discovery is actually incredibly valuable. It tells us that simply finding a planet at the right distance from its star is not enough. A planet needs to survive its star. It needs an atmosphere. It needs the right chemistry. And ideally, it needs some mechanism that allows liquid water to remain stable for long periods. That is why TRAPPIST-1e remains such an important target. It is roughly Earth-sized, appears rocky, and sits within the region where liquid water could potentially exist. JWST has been studying its atmosphere, but scientists still need more observations before they can confidently determine what kind of atmosphere, if any, surrounds the planet. If it has retained an atmosphere, the possibilities become extremely interesting. TRAPPIST-1 is also a fascinating place to imagine. Because the planets orbit so close to their star, many of them are likely tidally locked. One side could permanently face the star while the opposite side remains in eternal darkness. Between those extremes would be a permanent transition zone, a region of endless sunrise and sunset. If an atmosphere exists, winds could transport heat from the illuminated side toward the dark side. That could create climates unlike anything found on Earth. And if life existed there, it might have evolved under an entirely different kind of sky. The star itself is a red dwarf, so the light reaching the surface would be very different from sunlight here. Any hypothetical plants would not necessarily look green. Life evolves around the energy available to it. On another planet, evolution could produce colors, structures, and biological strategies that look completely alien to us. But JWST is not only finding potentially habitable worlds. It is also watching planets disappear. One remarkable example is WASP-107b, an unusually low-density world with an enormous atmosphere. Observations have revealed helium escaping from the planet and forming an extended structure around it. In other words, astronomers are watching a planetary atmosphere leak away. This is incredibly useful because planetary atmospheres are not permanent. Stars can heat,